I think we'll start again. It's one more or a short hour until lunch, but we'll press on to finish this session. My name is Bjarne Børresen, so I'm a mechanical engineer working normally in Multiconsult, but also I've been involved in this project as work package leader for work package number 6, so it's communication, dissemination, and exploitation. Also, I was involved already before. I was working for Energy Norway, so we talked a little bit earlier. I think we started back in 2014. We had the first. We were working to establish the Norwegian Hydropower Center. So we were participating in the Swedish Hydropower Center's assembly meeting in Sweden back in the spring of 2014. And this initial idea of collaboration for this EU project started back then, I think. So it's been a long road of first getting the application and now doing the work. So our contribution in this project is not as a research, but as communicating and trying to exploit the results. And that's what I'm going to try to talk a little bit about, because one of our deliverables is this, what we have called the Hydro Flex planning tool, which is a simplified tool, but trying to answer the question then, to flex or not to flex, to try to look at in the planning stage, how can I consider taking into account the cost of operating more flexible. So we had talked about, I think previously also, there is a huge change in the energy market worldwide, but also in particular in Europe. The Fit for 55 was decided last year, and Europe is having ambitious plans for transforming the energy system. And of course, with the recent events, both in terms of the energy crisis and also this security of supply, I mean, there's even more in focus on having control over the energy production and renewable, and in particular then variable renewable wind and solar is coming up as important contributions. And this challenge with these variable renewable is that they are missing this flexibility, so they are missing this ability. This is a kind of a definition of the flexibility, so the ability to, in a controlled manner, determine when you want to produce or respond to changes in the system. And this can be both on the production side and on the consummation side, so you can have also consumer flexibility. So at the, let's say, basic level, I'm a mechanical engineer, so I'm simplifying a lot, so I apologize to all the electrical engineers in the audience who have had courses on power system management. But from my simplified view, the basic level, we need to ensure balance between power production and power consumption. At the same time, we have to satisfy the power flow constraints, so it's also a geographical component of this. That's what we've seen from Peter and his presentation, that, I mean, in some of these simplified models where they talk about this copper plate, if you have perfect connection within all of Europe, you could easily shift from, or even larger, you can shift power from Sahara to Denmark, but in practice, that's not working. So we have to also look at the geographic distribution, and then you have to locally manage the voltage in the grid, because you have also this local property. And of course, from those planning the system, they have this both the predictable changes. They know the typical daily cycles, weekly, etc. I heard someone was working in the TSO, Nordic TSO, and they call it the badstutimen, the sauna hours. So in Finland, they can see this peak in about 8 o'clock because all the Finnish wants to turn on their sauna to have their evening sauna, and different kinds. It's where you can see interesting also from the Dinorvik power plant in Wales. They show these very interesting graphs, and there was like the interview with Lady Diana, and then there has the break where there is a commercial break and everyone is running, putting on the kettle, and you can see these huge spikes. So there's all this kind of interesting, and this is kind of predictable, but it's also kind of random. So how do we gain this flexibility? And this is a figure I've stolen a bit from work package 2. So we have, let's say from the market side, we have this future markets, which is basically a financial market, and we have the different power markets. So we have the day ahead market and the intraday market, which is the way in Nordic. And then we have on the very short term, we have the different system services that the TSOs are acquiring. So we have these different time scales in terms of the flexibility also. And in all, and let's say, as I mentioned also previously, we are, in particular in Europe now, we are in a tendency where we are trying now to make, initially here in the Nordic, we are developing this Nordic balancing model, developing a common Nordic balancing market, and with the long term, there seems to be a development toward a common European also market, where they are trying to then standardize. Some of the values here are just typical values, but again, there are differences. Like in the UK, my understanding is that in the UK it's a bit different. And also they have this ES4, what's it called, in Ireland, so different areas, and the different TSOs in US have, for instance, different also flexibility markets. So there's a lot of different market designs how you solve this, which have technical implications for our hydropower plants as well. But in Europe, and in particularly Nordic, it seems to be this convergence through this kind of system services that are in different manners are marketable. So looking now for the hydropower plant view of this. So what is this kind of impact for my hydropower plant? So I want to try to develop it more flexible. So some of the parameters that I am looking at and can develop or design or depending on the refurbishment project is this is the storage capacity, because that's the ability I have to shift power around. It's this wide operating range, so that's something which is both what Igor and Urban has been mentioning about, both these variable speed drives and what they're doing on the optimizing the design for operating at large range. We have talked about this rapid ramping rate, which was one of the 30 start-stop and increased ramping rate. I don't think we ever quantified that increase, which was the original goals of the hydropower Hydroflex project. And then we can also look at different technical requirements on the regulating or the stability, the ability to do large increasing the voltage regulation, the ability to run, for instance, at spinning reserve, so that you can run at, and then there are also you can run it in compressed air, so running it with drive, having low losses, but also having it just running at spinning reserve, ready to produce. And then looking at other types of services you can provide also. And this, if I consider this from my power plant, or in terms of a cost or in equipment I need, I can consider, I'm not sure if barrier is the correct, but it is what is opposing this in some sense. Of course, in terms of increasing the storage, that can be geographic. Of course, there is also environmental and also maybe social acceptance. But in principle, often you can increase it, but there is also a trade-off. You can increase also the regulating limits, but that means maybe that people having their fishing boats will have to, it will be stranded sometimes, or it's also a big discussion. So the tendency is that they wanted to reduce it, but that would we want from a storage point of view to increase that difference. Likewise, if we run at very wide operating range, we know that the Francis turbines traditionally don't really like to run below 50% maybe, or even 60% for medium head or low head Francis turbines. But we can do it, but it will have a cost. And likewise, the start-stop, we will have, on the large load changes, we'll have more pressure surges that are giving stresses on the turbines. Arne was mentioning that start-stops, or on the generator side, maybe the frequent start-stop is not so problematic because the machine is warm, so it's that thermal cycling. But you can see that if you had very few, that even if you're increasing it a little bit, that you maybe have increased stresses in the thermal cycling also. So trying to summarize this is a bit simplified here, but this matrix trying to see where what I've used there is the high impact on the different types of flexibility on the different components, or I consider it the medium impact where it's less expected to be less severe. Again, this is a very general view, and it's going to be specific for each plant, but it's a first impression. So this HydroFlex tool is then a simplified model to try to account for some of these barriers. So we have simplified, or this generic model for a power plant, Francis power plant, and the idea is to develop a tool that can illustrate the costs of different operating conditions or operating profiles. Actually, what I'm going to show is the different operating profiles. And it's a relative comparison, so we cannot, it's very difficult to get an absolute value. And it's always, we've been discussing this a bit over lunch before, because this, everyone wants to have these life expectancy models for hydropower equipment. But ideally, they want to have very high precision, but giving very little detailed input. So, and it's a contradiction. But what we can do here is to try to make a general framework that can give some ideas about this. And basically, it's based on this idea from fatigue analysis, where you are saying that different sums of different stresses in different regions, cumulative is eating the life of the unit. So here is just generalizing the kind of idea and not saying anything specific. What is the driver? We just said that each different kind of operating mode has a relative contribution to the using up the life of the turbine. So in this initial version of the model, we have a quite simplified hydropower system, and we compare this with or we define then a certain number of parameters to define the operating profile. So the operating profile is defined by the number of hours of operation per year, and the number of start-stop, and then percentage of operating within these predefined regions. So we have define this speed no load, so that, and then which is we don't, or spinning reserve. I mean, it's, we are not considering the electrical system here, so we do not really distinguish whether it's synchronized or not. And then we have this low partial load, and around the best efficiency, and full load. And in addition, we take into account the rapid load changes. We say if it's a load change of 25%, with like just using the full governor ramping rate, that's the rapid load change. And then we use a reference operating profile, which is at the moment we're still working on calibrating a little bit more, but basically it's a traditional high-head power plant in Norway, which has about 5,000 hours of operation. So maybe one start-stop per week, so 50 start-stop, and then mainly working around the best point, and then full load and very little operation at part load. And in this first example, then I'll just show you then with a different operating profile, which is we are now focusing more on flexibility operation. So typically we will have less operating hours, but much more start-stop, and also more operation both at spinning reserve and also part load, but then less operation at the best efficiency point. And in this very initial variation, we see that we get a 470% increase in the operating costs. So again, this is just a relative comparison, so I don't say anything what it's, so even, so in principle, if it will have very low cost, it doesn't mean that it's costing so much, but it's a relative increase. And the figure also is showing then the contribution in the model from the different changes. So even if I didn't operate that much at this speed load. Okay, so to the most to the left, but in the model at the moment, this is the operating which is contributing the most to the damage of the runner. So this is still not. We have still one more month before we are releasing the model on the website. So we have some more work to do to calibrate and fine-tune the model. In particular, we hope to try to incorporate some more of the results from the model testing, so that at least for the that we can get the latest model test results and have some discussions around that. At the moment, this rapid load change ramping is not fully implemented, and we will work one more round on implementing or calibrating and documenting the parameterization of the model. So this is a very simplified concept, but it can give some idea. I mean, if you are considering changing the operating pattern of your turbine or your plant, this can give some information about the impact. And it's the first useful tool. We've used this tool also for looking at installation of a large 1,000 megawatt solar plant in Uganda, how that's going to change the operating pattern for that plant. That was done with the power system model, where we did that, and then we can see how that changed the operating pattern for the hydropower plant, and then we could look at how this would change the operating cost for their installed fleet in no, it was in Zambia, not in Uganda, but on their installed fleet. So this is a conclusion. So it's a purely empirical model, so we only get data out from what you put in terms of the parameters of the cost of the different operating regions, which is what we have done. Is, I mean, we don't have any model testing or test rig, so what we have done is to go to the literature and look at all the different publications on what different simulations and different experimental results are published, and then try to aggregate that. And it's also a deterministic model, so it doesn't account for, I mean, this is clearly a stochastic problem, so it should be probably looked at a more sophisticated stochastic model so that you get kind of a probability distribution instead. But it's an initial attempt. And I think it's a simple framework that we can use to evaluate impact of the operating profile. And we can use this then as an initial relative comparison to see if I'm changing my operating profile, how is that impacting, can I expect that to impact my cost? And we can start then to pull out if we can get a good model for some of the systems. We can try to combine that with a simplified model, and then maybe have, when we have more advanced digital twins, maybe for the turbine, try to combine these together. So that's the conclusion of my presentation. Thank you very much. Urban.
In the flexibility list that you had, what constitutes a flexible power plant, power wasn't part of that on your list there. The amount of power, do you consider that as a given, or because increasing the power in power plants can add flexibility?
Yes, you're right. I agree. So that's that. But in this case, it's taken as given. What we have seen, I mean, a lot of cases, and that you can compare, for instance, hydropower plants in, as I said, typical Norwegian hydropower plant have somewhere between 4,000 and 5,000 hours operation, and I think a typical Swiss have between 1,500 and 2,000 or something. So because they've increased the capacity so much and they're much more focused on peak power. So in some sense, you get it in terms of the in the model, you get it in terms of reducing hours and then changing the profile. But you're right that yeah.
A question for can you introduce the results coming from the runner now for from the strain gauges? Can you bring that into the model and then utilize that results, or will you do it?
Yeah, that's my. Hopefully, we can do that so we get the results in time. And basically, this is what we've done. So look at different publications on and their statement on how different operating patterns are impacting the stresses.
Have you been considering the role for hydro? I mean, there are alternatives for providing flexibility, like batteries and superconductors and so on. Should hydro aim for all because we can, or can it be more cost efficient to do some ancillary service with the batteries and things like that, and focus on the time scale where there is no competition?
Yes, I think there are two answers to that question. Clearly, I mean, probably a large reservoir hydro, the biggest value is the energy storage and the ability to shift in time and be dispatchable at a given time. But I've been thinking a bit about also, I mean, this. We have, for instance, looking at this either with the electrical systems on what was presented before with the fully converted solution, also with the you could think that the battery, in a cure we had like a mechanical storage to smoothen out, but you could think that a battery solution would also be able to smoothen out the variation, so you could still provide a lot of flexibility services. And again, that maybe my understanding is that, for instance, this huge Tesla battery that was installed in Australia, ahead of time they had a very good solid market for this kind of system services, but that battery in itself was so huge that basically the market collapsed. And I think it's similar that there are work in Norway on testing out this fast frequency response FRR market, but the volume is quite small, so at the moment you cannot really justify building a huge battery at a large power plant in Norway only on serving that kind of market, but maybe you can combine it with serving that kind of market, but also operate your turbine in a more or less severe case. So maybe there are some yes and no answers to that question, in my opinion.
I'm still questioning. I think that the fast frequency response market can be something that we can utilize from the hydropower side, because we can provide larger amounts of power in a short time than the batteries can today. And I don't know what the biggest battery is right now, but I heard up to 20 megawatt. Maybe there are bigger ones.
The Tesla battery is 100 megawatts,
okay.
If I understand correctly, and 110 megawatt hours or something. So it's basically 1 hour operation at full peak load.
But when you said about where we don't have any market competition, I think for the high power outputs needed in a short time, maybe the hydropower system is more flexible than or maybe cheaper as well than batteries in the future. I have no answer to this, but that's my gut feeling, I would say.
I don't have so much experience from the let's say the utility grid and so on, but I have some experience with battery from ship propulsion and so on. And of course, it is always like if you want to have a battery, you have to charge it and you have to discharge it, and that is losses. So what I feel maybe could be interesting with battery is to have, let's say, the virtual inertia thing and so on from battery, because then you are not supplying energy in average, just dynamically. While, for instance, if we are looking on our system with the full power converters, if we are going to supply virtual inertia and so on from the hydropower plant, we have to have margins in converters and everywhere to provide the dynamic power as well. But if you, for instance, had a battery in parallel instead, taking the inertia effects and the damping, you could, let's say, be closer to the maximum rated power in the converter chain. So I think maybe that is cheaper way. I can tell about this spinning reserve. That is an interesting thing for batteries, because we have been working with, I have experience from this with some large supply ship and drilling ship and so on, and or offshore support vessels. In this case, for instance, if you have a DP3 operation, it means that you have to have 3 generators in operation due to safety. And that means that they're all running at low power, so they have very bad efficiency. But then it was it was allowed to have only 1 generator producing the power, and the battery is only spinning reserve. So it can take, if that generator or diesel engine is tripping, the battery can take over the production immediately until you start the next generator. And I think something like that is interesting in the power system as well, I think. So it's very short operation of the battery, because they use the battery as a main source. I don't think it's wise, because then you have to take the energy from the hydropower station into the battery and out of the battery to the load. That is losses you don't would like to have. You want the shortest way from the energy source to the user. That is the best, I think.